This is lecture 10, chapter 4. This is a continuation of equilibrium that we discussed in the previous chapter. I want to continue doing examples showing you how equilibrium can be achieved or is achieved by, and forces can be determined simply by using the three fundamental equations of summing the forces and summing the moment. Now, one thing that's new in this compared to the last, in lecture 9, was the concept of what is a two-force member or a two-force body. Now, you'll notice in the image that I've shown that the forces 1 and 2 in A are pointing in different directions. And then if we look at B, they're also pointing in different directions. If that is the case, then this bracket would not be in equilibrium. So only when the forces point equal and opposite to one another can this bracket be in equilibrium. And so the idea then is if you have a system in equilibrium and you have this type of structure, you will have a known direction for the force. So I want to explain that in a little more detail. If you were to say, let's say take something really simple like just a single piece of steel, in a linear piece of steel, that if we attach it here and we attach it there to some outside component, then the only way that this can be in equilibrium is that the force is either going this way, like that on each end, or if the forces are going like that on each end. So this, in this context, this member would either be in tension with the arrows going away or be in compression. If it wasn't the case, if let's say, for example, one force is going that way and one was going that way, then there would be a net rotation or a net moment on this. There would also be a net force in the X and a net force in the Y as these are going in different directions. So this can't exist in statics, at least as a two-force member. I mean, it can exist, but the member won't be in equilibrium. Now, it doesn't just have to be linear. If we have something that's, say, a quarter circle like that, then in that case, as long as it's only pinned in two locations and there's no force applied from the outside, so then the direction of the force on this quarter circle would be through the lines, so through the pins. So if it was shaped like this, it would go through there. If it was shaped like this, but pinned, let's say it's this and this, and if it's pinned here and pinned here, then the temptation to say, well, this end, but it's not pinned at that end. It's as if this doesn't exist, so the force has to go through here. So anytime you see this type of structure, you can know then, because it's a two-force member, you know the direction in which the force is going in. And so that allows you then to relate the force in the X to the force in the Y by some fraction based on this geometry. So let's look at an example of that. And in this case, we have a simple landing gear, and we're given the loads that are applied to it. So you have a 6 kilonewton force that's applied to the wheel going up from the ground. You have a 2 kilonewton force to the right, that's the braking force. And then you have this main strut C, where it's pinned at C. And then you have the strut AB. So AB meets the definition of a two-force member because it's pinned at A, pinned at B, but there's no externally applied force to it. The same can't be said for the longer member that goes from C to A down to the wheel. That has applied forces, therefore it's not a two-force member. Now, to solve this problem, what we're looking for is what is the reaction at C and what is the force that's actually acting in AB. Now, because we know the direction of the force in AB, we're able to solve. We wouldn't be able to do that if we didn't know this was a two-force member. So here what I've done is I've actually drawn a quick schematic of the problem. And so in this case, we have our forces labeled. This is our free body diagram. We have our X and Y component of C up here at this end. And I've put in some dimensions. We know it's 1,000 millimeters from top to bottom. And using the 20-degree angle and tangent, I can determine that this side of this triangle here is 364 millimeters. I also know that if this is 20 degrees and this angle here is 30 degrees, that means that this total angle would be 50. Therefore, this angle has to be 40. So I know that my force AB is 40 degrees above the horizontal going in that direction. Therefore, if I were to look at just the force AB, if I were to cut this off and put it down here, I can see that the force AB in the X is just going to be AB cosine 40. ABY is just going to be the force AB times sine 40. And the respective distances, this height up here, which is this here, is 400 millimeters. And using tangent, again, I found that's 145.6. So now that I have those basic dimensions, I can go ahead and solve. Now, remember that we have our three fundamental equations. We can sum the forces in the X, we can sum the forces in the Y, and we can sum the moments. And we can do that for any system. Now, X and the Y to 0 is fine. When we sum the moments, we have to pick a point. Now, remember what I said last time, that you want to pick the point with the most unknown. So in this case, we're going to choose C, because that gets rid of 2 of the 3 unknowns that we're looking for. Now, whether you do the moment equation first or these first doesn't really matter. What you'll find is you're going to have to do them all eventually. So if I go ahead and I write out some of the forces in the X is 0. And if I write that out, I get 2 kilonewtons. Actually, I'm going to put it in 2,000 newtons. And then that's going to be plus FAB cosine of 40 degrees. And that's going to be plus the X component at C. And I'm just assuming it's going to be positive. I don't know for a fact, but it'll come out in the wash later if it's not. So there's my equation. I'm going to leave that there. I'm going to skip a space because we're going to come back. Once we know a force AB, we're going to come back and solve for C. So I'll go ahead and sum the forces in the Y, get that equation. And if I do that, I have 6 kilonewtons plus FAB sine 40 degrees plus CY equals 0. So now I have those 2 equations, but you notice that I have 1, 2, 3 unknowns. So I can't solve yet. So the next one is going to be the moment. So I'm going to sum the moment about C to 0. And since I already calculated my distances up here, it's going to make it a lot easier. So if I'm summing the moments about C, you can already notice that the 2 kilonewtons times this 1,000 millimeters is going to want to make a rotation that's counterclockwise. So the 2 times 1,000 is going to be positive, whereas the 6 times 364, because we always go by the perpendicular distance, that's going to be a clockwise moment, or negative. And then we can then break this down. We know that this is going to consist of a force going up like this. That's going to be our sine FAB times the distance 145.6. Again, that's going to be a clockwise. Whereas the CX, C sub X, or the X component of FAB, or sorry, the X component of FAB, not C sub X, is going to be going counterclockwise. And there's our respective distances. So I'll go ahead and write those in. And what I end up with is 2,000 newtons. No, sorry, I should have left this as. I apologize for mixing that. 6,000 should have been up there too. I'm changing my notes as we're talking. So 2,000 newtons times 1,000 millimeter. And then that's going to be plus, and I'm keeping the positive moments together. So FAB cosine 40 degrees times 400 millimeters. And then that's going to be minus 6,000 newtons times 364 millimeters. And that's going to be minus FAB sine 40. And that's going to be times 145.6 millimeters. All that equals 0. So this plus this minus that, all equals 0. That's everything. So I solve, I get my FAB, force in the AB direction, is going to be equal to 865 newtons. So now that I have that, I can come back up. I can take this value, the 865, and I can come back up, plug it in here, solve for that. So I don't need to show you that, but when I do it, I get CX or C sub X equal to 2,660 newtons, but it's negative. So it comes out to be a negative value. And so when I write it as negative, and so what that means is that I assumed that it was going in that direction. So that means it's really going in that direction, which makes sense because I have 2,000 newtons going this way, and I've shown that FAB is going that way. So it makes sense that the X would have to countermand that or counteract that in order for equilibrium. So I know that's 2660, or I could write it as 2660 newtons and with an arrow going that way. So that's an acceptable way to write it also. CY, that ends up also being negative. It ends up being negative 6,560 newtons. And so, or you could write CY equals 6,560 newtons and going down. So the important thing is that if it does end up being negative in these cases, rewrite it with an arrow. You can leave it negative, but usually this is a little more easier to see, especially during grading. It makes it no doubt what direction you're saying. Don't, though, go back here and change it. So you don't need to erase this and point the other direction. That'll just confuse it. Just leave your free body diagram as it is. Okay, so that's that problem. So let's go back. And now we can look at the second type of problem here. So here's a problem off your worksheet. And this is a crane boom. It's very similar to the one we just did. So you can see that you have the boom, the BC is the supporting hydraulic to move that. And it is, again, a two-force member because of the fact that it's only connected in two places, B and C, and there's no externally applied force. This whole boom pivots at A, and then attached to it, you have the mass of the boom, which is at the center of gravity G, 4 feet from A, and then you have the statue that is 8 feet away. Actually, it's 9 feet away from A, it's 8 feet away from B, and then add the extra foot. So it's a 9-foot distance total. So again, we want to solve this. Sorry for the little is lifting the TR at the end. That's a typo. But we're trying to effectively determine the reaction at A and the moment, or I'm sorry, the force in BC. So having done the other one, you should have no problem doing this on your own. And that's what I would recommend. I would pause the video at this point and take a stab at it. And then once you're ready, come back and look at the actual solution. Okay, so you've probably looked at it, you've conquered it, that's good. So we know that this distance to this distance is 8 feet from here to here. That's point G, so not a 6. So let's go ahead and how do we do this? Well, just like before, we're going to sum the moment, sum the forces. So on this one, I'm just going to start off, I'm just going to say sum the moment about A to 0. I could have done this in the last problem also. Whatever you choose, there's no incorrect way whether you start with the forces or start with the moment. But if I do that, I notice that force BC cosine 40 times 1 foot. So that's the horizontal component is only 1 foot. It would be basically this here, 1 foot away from A. And the same with the vertical. So FBC cosine 41 foot plus the force in BC sine 40 times 1 foot. And then that's going to be counteracting the 125 pounds that's at a total of 5 feet away. So that's correct. Actually, no, I apologize. That's 4 feet. The total distance is 4. It says it goes from here to here. But the Trump statue is 9 feet, so plus 600 pounds times 9 feet equals 0. So we solve and we get the force in BC gives us a force of 4,190 pounds. Sometimes you'll see that written as 4.19 kip. All right, or 1,000 pounds. So we can do the same thing as before now. We can sum the forces in the X, 0. And in this case, the only force in the X is the reaction at A up here and the X component of BC. So whatever the X component of BC is going to be equal to the X component A. And since we've determined that BC is pointing this way, it has to in order to balance out these moments, then we know A is going to go the other way. So if I write this as AX plus FBC cosine 40 equals 0, and now I substitute this into that, I get AX equals 3,210 pounds, but I get a negative. You can see that from the equation. So really AX is equal to 3,210 pounds. And again, using the sign convention to the left. So doing the summing the forces in the Y, we do the same thing. In this case, we have AY. And now that's going to be included plus, now in this case, it's going to be FBC sine 40. But then we have to account for the weight of the statue. So minus 600 and also the weight of the beam minus 125. That equals 0. So we solve and we get a Y equal to a negative 1,967 pounds, or effectively AY equals 1,967 pounds going down. Okay, and that's that. All right, so looking past this, we also have the concept which is called a three-force member. Now, the three-force member is similar to the two-force member in the only sense is that if you have multi-forces acting on a system, they have to go through the same point. So the two-force member, in order to be equilibrium, the forces had to be collinear and have opposite sense. In this case, the three forces must come to a single point. So, for example, if we look at that same idea, going back to this, if I have an object, like the blob, then what I found is that if I want it to be in equilibrium, then all the forces have to, when you extend them, have to meet at a single point. And so because I know then if I were to draw these, I would get a force going this way, force going that way, and a force going that way, wouldn't I? And so that would be the closed triangle system that we talked about in chapter 2. So this concept can be used to solve problems that otherwise would be difficult to do, but it also can be used to apply force triangles to solve problems. Now, I want to show you one example of force triangle use in this next problem, and you can decide whether you think it's an easier way or if it's just convoluted, but I'd like to introduce it so that you at least have more than one way to skin a cat, so to speak, or fry a fish. So we look at this. Let's go ahead and next page. So here's our problem here. All right, so as I said, this next problem, it's not a complicated problem to solve. It's just it's interesting because this is a good example of how we could use a force triangle to solve it. And so go ahead and switch, and I want to show you how we do that. So if we look at this problem, we can see that we want to find the reaction. Well, actually, before I even get to that, as I said, you can use a force triangle or what I call 3 basic equations. That's summing the forces in the x, summing the force in y, and summing the moments about a particular point. So this problem's on your worksheet, and what it says is you have this rod AB sitting in the corner. So the reaction A is composed of an x component and a y component, and then you have this tension BD that is connected at B. So you have 3 unknowns, and so we have 3 unknowns, but really we have 2. We have the reaction A, and we have the TBD, and we have another force 150. So because we have 3 forces present, because A being broken down to x and y doesn't count as 2 forces, it's still a single force because we can know the x and y components, we can use a force triangle for it. So I'm going to show you how to do that real quick, and then we'll do it the conventional way. So first off, here's our drawing we have, and we know that this is 240 and this is 240. So those are our millimeters, and that goes out to this point. And this is B, and that's D, and that's A, and then our force here, 150 newtons, is a point C. So first thing we want to think about is if we know that if we have a system, kind of like when we had our blob, we knew that all 3 forces went through a single point. So that has to be true here also. So what does that mean? Well, so conceptually, we know that any force we draw is an infinite line. So we could take this 150 newtons and draw it like that. Now you notice that when I do that, it intersects here at dB. Now we're told that this 150 newton is at the midpoint. So because of that, we know that it's going to intersect the midpoint of this line, or we know it's going to intersect 100 millimeters above B, since the total distance is 200. Now, you may not have noticed, but this is a 5, 12, 13 relationship. So if I draw TBD, this point here, I'm going to have the horizontal component's going to be 12/13 of TBD, and the vertical is going to be 5/13 of TBD, and this will become important shortly. So I have that. Now, in order for this to be like so, that means my reaction A must go through that point. So I can go ahead and do this. And now I know the direction of A. It has to go through there so that it is in equilibrium. So then probably want to know what that angle is. Well, fortunately, because this goes to the midpoint, it makes it quite easy. I know that this triangle here, the base is 240 and the height is 360 plus 100. So that means that tangent, inverse tangent of what is 460 over 240 equals my angle alpha, I'll call. So in this case, alpha is going to equal 62.4 degrees. There I have it. So I have that angle. So I have that, and the other thing I might want to figure out is what is this angle? That'll become important with my triangle. So that angle there. Well, I know that this distance, the base of this triangle here is 480 and the height is 200. So if I call that angle gamma, I know that gamma equals the inverse tangent of 200 over 480, which gives me a value of 22.6 degrees. So now let's go ahead and draw our forced triangle. So I've kind of moved it down here. So what I've done to get the forced triangle, first I drew, as whenever you do a forced triangle, first you draw the either vertical or horizontal line. So I drew the vertical. I know that then that's going to have to connect to something. Now, I could have drawn at that point, I could have drawn this line here. So it could have come like that. And then I would have drawn this line up there. So it would have just been a mirror image. So it really doesn't matter how you connect it. Since I'm right-handed, it seems more logical to draw it this way. So I went ahead and connected my A there. So again, A being this line, that's my reaction. And so there's the angle 62.4 because I know that. And I know this is at 90 degrees, so therefore that has to be 27.6. I know that this is an alternate interior, so that has to be the same there. I calculated this here, that's 22.6, that's gamma. And therefore, if I add everything up and subtract from 180, I get this to be 67.3. So then real quickly, I can use the law of sines, right? So I know that TBD over the sine of 27.6 has to equal 150 over the sine of, and when you add that together, you get 85 degrees, which equals A over the sine of 67.3. And you're done. So really finding this was the time-consuming part. This comes out really easy. So when I do the math, I end up with TBD equals 69.7 newtons, and A gives me a value of 138.9 newtons. And that's it. So that's one way to do this problem. We could also do it the other way using the conventional method, and that works just as fine also. So coming back up here, I can see that, let me pause for a moment and redraw this. So there it is, drawn. Now, remember I said that these would be important up here. So what I've done is I've taken tension TBD, and you can break it up anywhere you want, really. You could break it up there, you could break it up there. But if I break it up and move it all the way to here, then this vertical component no longer has any contribution to the moment about A, and it's all just one. Whereas if I did it from this point, it would be 5/13 here, but then it would be multiplied by this 480, but the 12/13 component would only be multiplied by 360. but it works out the same, so it really doesn't matter. So if I use a conventional method, I'm going to sum the moments about the point with most unknowns, being A. So I have 12/13 times my tension BD times the distance 560 millimeters. And that's just going to be minus 150 newtons times 240 millimeters. And that equals 0. So I end up with my TBD equal to, I think in this case it's 69.6. When I did it with the force triangle, I got 69.7. That might have had to have been a rounding error. But again, I'm not going to quibble over a tenth, close enough for government work. So proper number 3 sig figs, so we're good. So then we're going to go ahead and sum the forces in the x to 0. And we know that that's going to be AX minus 12/13 TBD equals 0. So we're going to get A in the X is going to be 64.3 newtons. Do the same thing. Sum the forces in the Y to 0. In that case, we're going to get 5/13 TBD minus 150 newtons plus AY all equals 0. So we get AY equal to 123.2 newtons. So the only difference in this problem is that we come up with A and X and Y components, whereas previously we had A equal to 138.9, and we had it at an angle of 62.4, I believe. The angle 60, yeah, 62.4. So same thing. If I said inverse tangent of 123.2 over 64.3, you can check it. I'm sure that I would get 62.4. And if I square root, found the magnitude, I get that. So either one's acceptable, magnitude, direction, or component form. So I hope you see how both methods have their advantages. Again, when all else fails, if you don't like the triangle, you can always do it this way. This always works. The triangle only works if you have 3 forces. So that's the big limitation. All right. And that's it for this lecture. So I'm going to do a short lecture for lecture 11. That's going to include a few problems from the same section just to mop up and make sure you understand 2D. Lecture 12, we will be covering 3D, and that'll be it for next week because we're going to have our midterm. So the just coming up is the midterm is coming up. I'll put the date on Canvas, but we will be having midterm, and it'll be through the end of chapter 4. So everything up to that will be included on it. So thank you, and I'll see you next time.